Thanks a lot for the kind introduction. Thanks for having me. It's been a great workshop so far. I very much enjoyed the discussions. I think it's really great to have the RL and controls community meet. And this workshop really contributes nicely. Thanks all of you to stick around. I guess it's nearing the end of the day. Today, I'd like to talk a little bit about safe and efficient exploration, connecting to a number of themes that we've seen throughout the day, but hopefully contributing to the discussion. Given that this is the end of the day, I'll try to provide some light entertainment. So it's not going to be an overly theoretical talk, but happy to go into more technical discussions afterwards as well. And of course, this is joint work with a fantastic set of PhD students, postdocs, and senior collaborators who I'll acknowledge as we go along. No, I guess I don't have to say much more about RL, right? Obviously, this model that's advertised as an agent that changes the world, hopefully trying to derive some reward along the way. As we all know, the poor agent doesn't know how the world works, right? So it faces this dilemma of experimenting with actions to learn about their consequences and using what it learned in order to do better, right? And of course, these feedback loops are central to ideas on control, right? Approximate dynamic programming, adaptive control, and the likes. Now, RL certainly has been at the heart of a number of breakthroughs, and we've seen some of them already mentioned in Hackett's talk. You're all familiar with them in the context of gameplay, also in robotics now, right? So our colleagues at ETH use DeepRL to have robots go hike in the Alps, so they finally also get to enjoy that. Colleagues at the University of Zurich use DeepRL to fly drones faster than human pilots. I'm sure you'll see plenty of super exciting robotics research tomorrow in Jan's talk. So I think it's super exciting space for RL. And so what's certainly remarkable that DeepRL is really this very powerful computational hammer, right? That allows to scale to very large and complex high-dimensional continuous state and action spaces. That said, even though RL is sort of advertised as this model of an agent learning by interacting with its environment, that's by and large not really how it's practiced, right, in a lot of these applications. Right? And so a fundamental requirement is really to have an accurate simulator. Perfect examples are games. We know precisely how the go board looks once we and our opponent have taken a move. In robotics, for tasks like robotic locomotion and so on, you can actually build very sophisticated, very accurate physics simulators and get very far using that sort of machinery. But if you think about some of the applications where you might want to think about using RL and data-driven control and the likes, maybe in precision agriculture, maybe in smart mobility, maybe healthcare applications, maybe more open-ended learning tasks in robotics, interacting with humans, it might be hard to really get an accurate enough simulator. And if you think about scientific applications, the whole reason we do science is to learn how the world works. And so now, in these sort of settings, exploration, of course, not just as a computational concern. Right, that's where existing policy gradient algorithms really shine, right? To efficiently search very large and complex state spaces in a computationally efficient manner. But here in these settings where we don't have a perfect computational model of the world, exploration becomes expensive. You might have to run experiments, physical trials in the real world, and become safety critical. And I would argue, if you don't really know how the world works, every action we take is exploratory in nature. Okay, so it's not even about sort of dedicated, explicit exploration that we might want to carry out. So I want to talk about some ideas that we've been exploring in my group together with our collaborators. And I'll start with a model that we call safe Bayesian optimization that will build on and lift some of these ideas in the context of RL in the main part of this talk. And so here's a motivating application. So we actually talk about an application. So this picture here shows the Swiss fell-free electron laser. It's a scientific facility operated by the Paul Scherrer Institute, a large research facility in Switzerland. It's a 700-meter-long linear accelerator that generates X-ray pulses of extremely short duration, femtosecond duration, 1/millionth of a billionth of a second. So you can use this to image extremely fast processes like molecules transforming in the context of a chemical reaction, right? With lots of applications from material discovery to drug design and the likes. It's also a very complicated machine with many literally moving parts. So the beam properties are carefully shaped by magnets that can be moved around. They depend quite subtly on different environmental conditions like temperature, humidity, and the likes, and need to be adapted to application-specific requirements. So you don't just set this machine once and off you go, but you really have to kind of operate it as it's going. And of course, to some extent, one can simulate the underlying physics, but it's hard to really capture these ambient effects of temperature and humidity, and simulations are extremely slow. Okay, so we really would like to do this while operating the machine. Okay, and now kind of a very coarse abstraction. You can think about this machine as a big black box. I don't know too much about the physics behind it. And we can inject a bunch of tuning parameters, theta t, and get some reward measurements, right? Maybe beam intensity or how close we are to the application-specific requirements. But we also have to be careful with what we do. So if you're not careful, then there can be beam losses that damage the magnets and might actually really hurt the machine. And our collaborators wouldn't let us use our algorithms anymore. Okay, so fortunately, there's a bunch of sensors spread around this device, and we can monitor how close we get to violating any of these safety constraints. Now, the trouble is neither the reward nor the constraints are known ahead of time. That means that basically from observations we make along the way, we need to close the loop to drive experimentation. Of course, hopefully in the end, we'll find a good solution, right? Satisfying application requirements, but not just being safe at the end, but we want to ensure feasibility along the way. So basically, we have to solve a non-convex optimization problem with non-convex constraints with stochastic zero-order feedback while ensuring feasibility of all the iterates. So it should be pretty obvious that in general, this is a completely hopeless task. Okay, so we'll have to make some sort of assumptions, and that's sort of what we're going to talk about. Yes?
But why the art is unknown? Is it that it is completely unknown, or is that it's switching between different reports depending upon the operation of the system?
Yeah, it's basically measuring, right, the beam properties during the experiment, right? And how close is it, the intensity to the target requirements. That's sort of the abstraction maybe that suffices for this talk. You can measure it online, right? You can't just say, if I were to use that parameter, that's what I would get. Maybe let's leave it at that. Happy to discuss this more afterwards, okay? But so it's basically something we can measure online through an experiment, right? Similarly, you can measure kind of how close we are to violating constraints, but there's no nice functional forms or so, right, of the reward or the constraint that we have. So that's basically where the challenge comes from. Okay, so we said we need some assumptions. Now, one natural way of encoding assumptions is the Bayesian paradigm, right? So we can sort of try to endow the black box with a prior distribution and then use the uncertainty in a prior in order to navigate this exploitation dilemma to find good rewards while hopefully thinking about finding safe and feasible solutions along the way. And so that's, of course, the key idea behind Bayesian optimization. And kind of the main principle behind it is, of course, the following. So suppose we have already collected a bunch of measurements so far, shown by these pluses here. We can construct our posterior distribution over these functions, maybe the reward function for now, and predict kind of the uncertainty in the objective as well, as shown by this gray shaded area. And if the model is well calibrated in the sense that it covers the true unknown objective in this blue dashed line here, then you can apply this following logic, right? So we can look at the pessimistic estimate of the optimal value, right? That's this green dashed line here, maximizing the lower confidence bound. And then we can rest assured that the maximum must be somewhere above it. So if we go look for it, we can sort of focus on this green region of sort of the plausible maximizers. And that's an idea that's central to the analysis of algorithms and bandits, reinforcement learning, and the likes. And so one way to implement it is to basically kind of justify the optimism in the face of uncertainty principle, which is sort of an acquisition function, right? The function that you can optimize as a surrogate that takes the uncertainty in this posterior into account and we'll just pick the point that maximizes upper confidence bound. Okay, I don't think I have to say too much more about optimism. We've heard all about it throughout today's talk. One slide I want to briefly elaborate on a little bit is the following. So central for this logic, and maybe even more importantly, if we want to think about safety, is this notion of sort of calibrated models, right? Can we sort of get coverage, right, for some unknown objective or unknown constraints we care about? Okay, now if we sort of really kind of have a prior and believe that the nature really behaves according to our prior, calibration is given through the process of Bayesian inference, right? So our posterior distribution, right, basically will govern the distribution over the samples conditioned on the data we've obtained so far. But maybe that's a bit of a strong assumption, right? That we really have a perfectly calibrated prior distribution. And so the true objective might live outside of the credible sets of this Bayesian model. And now there's been quite a bit of interest in sort of trying to calibrate and sort of give frequentist analysis of these Bayesian models. And to some extent, that indeed is actually possible. So one can basically sort of calibrate these confidence sets in a way blowing up the credible intervals of this Bayesian model in order to get frequentist coverage. So uniform across the domain and across the steps of the algorithm, even for adaptively collected data. And the way kind of one has to blow those up depends on one hand side on the complexity of the unknown function measured in the case of Gaussian process priors that are very often used for Bayesian optimization in the reproducing kernel Hilbert space norm of the unknown function f. And some notion of complexity, right? So capacity of this prior distribution, some notion of effective degrees of freedom. So you'll see that in some of the later slides. I'm not going to go into much more details than that. Apart from, if you sort of deal with Gaussian process models, we have a fairly decent understanding by now sort of under what circumstances one can get sort of these calibrated models. Now, of course, in the practice, you might want to use neural networks and certainly quantification and deep learning. We've seen a bunch of examples of models in David's talk earlier already, right, where this is being done. And there, this is very poorly understood. So there's many interesting open questions on how one can do reliable and certainly quantification deep learning. One can get take first steps by through the neural tangent kernel analysis. But of course, they only, to a very coarse approximation, describe what's really going on. So now we talked about sort of optimism, right? Optimism in the face of uncertainty. If you think about safety, being too optimistic is maybe also not the right way to go. So if you have now this constraint optimization problem, try to find this constrained optimal solution where kind of our constraint now needs to be above this dashed line here. A natural idea is to now, of course, apply that same rationale, not just to the objective, but also for the constraints, right? And now think about kind of pessimistic estimates of constraint satisfaction. So this red set here is sort of a statistical inner approximation of the feasible region. And as long as the model is well calibrated, as long as we only sample sort of within this red set, sort of we should be safe with high probability. Okay, and so now a natural first idea would be to say, let's apply standard principles like optimism, but restrict ourselves to this red set, right? Maybe want to optimistically select the action or some other plausible optimizers, but always constrained within this red set. Now, one challenge that arises is the following. So what often happens is that plausibly optimal actions might be contained in the strict interior of this red set. So it means that if you now keep sort of sampling this green set only, right, a set of plausible optimizers, if you're only optimistic, there's no incentive to kind of explore the boundary of this red set, to sort of expand that red set. Okay, so it means that in order to solve this problem, one actually has to explicitly think about this notion of expansion. Okay, and so one way to do so is to basically think about a set of actions that allow to plausibly infer additional actions to be safe. And as long as you kind of sample both those and plausibly optimal actions, one can actually, with the right selection rule, for example, just maximizing the most uncertain action among the red and the purple set, pick an action so identify eventually an action that is arbitrarily close to the kind of the optimal reachable solution and guarantee safety along the way under these kind of well calibratedness assumptions that I've described to you before. It's the first algorithm. There's been now lots of developments since the first algorithm. It actually also really quite nicely works. So this picture here on top shows my former PhD students, Moimir Mutni and Johannes Kirschner, and our collaborator, Nicole Hiller, in the operating room of SwissFel running the algorithm on the machine. And so they did a whole bunch of runs tuning this device, really outperforming sort of standard heuristics that were used in this domain. Before, that often got stuck in sort of suboptimal solutions. And there's been lots of follow-up work tuning parameters for different robotic systems. There's been a really nice application by folks at Caltech on using algorithms from safe Bayesian optimization in application to medical rehabilitation and so on. So there's basically now a number of kind of applications of this kind. Now, one of the key sort of shortcomings of Bayesian optimization and also safe Bayesian optimization is that it's typically sort of restricted to relatively simple policies, relatively low dimensional domains. where essentially you have a sort of small number of knobs you can turn. So in this example I showed you for the Swiss laser, it's sort of 24 tuning parameters that we were controlling with this algorithm. If you think about learning complex behavior, right, of the type that reinforcement learning algorithms can learn, you might want to use neural network policies with millions of parameters, right? So no way to get there with Bayesian optimization. And so what we've been very interested in for quite a while is how can we push ideas from Bayesian optimization, but sort of try to make them work for RL. Okay, and so what we're going to try to do is to basically kind of leverage these ideas of, first of all, uncertainty quantification to kind of now not just quantify uncertainty about the reward, but also about kind of the dynamics. And most importantly, thinking about what's the right kind of surrogate objective or acquisition function that we should optimize in order to make those work for much more complex behaviors. And of course, what we'd like to do is we'd like to kind of be able to use state-of-the-art algorithms from RL, right? Kind of use the deep RL policy gradient hammer. Okay, and so to that end, we're going to take a model-based approach, I think very idiomatic, right, to focus on control. So what we're going to do is we're here in this illustration actually focusing to unknown deterministic systems. These ideas can be generalized to sub-Gaussian dynamics as well. And for now, we'll assume the rewards actually known and known to us. We can also extend this where the reward function is unknown as well. So the main uncertainty here really is in kind of the next states that we might end up when picking actions AT in state ST. And so that's what we're going to try to model, right, with our probabilistic model. And now, if we had such a well-calibrated model, and we can get it to some extent if you use Gaussian process dynamics with the way we've described, we can sort of apply this coloring rationale. We can sort of try to use it for exploration by forecasting the consequences of picking sequences of actions, either through MPC or policy search, and maybe try to come up with an optimistic policy that maybe reaches a goal or gets a high reward. But of course, nature might not quite work the way that we intended to. But hopefully, we're going to collect some useful information along the way. Our uncertainty is going to contract. And as a consequence, we'll be able to act kind of better in terms of rewards after incorporating that observation. Right? And that same idea that can be applied to exploration can also, of course, be applied for constraints. So if you have some designated set of unsafe states that we want to avoid to visit, then we can basically do robust optimization or sort of formal verification with respect to this plausible set of dynamics that are supported by the statistical model, trying to avoid these unsafe states. That's kind of the cartoon picture of what is to come. Okay? And so to that end, right, we'll start the starting point is Bayesian optimization. So we want to lift this to kind of Bayesian model-based RL, even though kind of we would analyze it from a more frequentist perspective. So we'll follow this loop that we've seen discussed before. Emily also talked about the same online RL model in her talk earlier this morning, where we basically would iterate over a bunch of different episodes. What we're going to do is we're going to explicitly quantify the uncertainty in this dynamics model. So we'll start with the prior, might be an uninformed prior. We'll talk a little bit later about how one can build in a bit more domain knowledge into that prior. Maybe no initial data, maybe there's a bunch of behavioral data collected from other policies that we get to know about. And now we iterate over a bunch of episodes. Every episode, we're first going to incorporate the data we have to obtain a posterior distribution about the dynamics model. Then we would use it in order to update our policy. You get a policy pi n in episode n. And then we would roll it out in the real environment. And that's sort of what matters, right? So that's where we want to be careful, right? You want to minimize the number of episodes to use, right? You want to really minimize, kind of avoid taking unsafe actions. In that step, this is where we collect additional data, we add it to our data set, and we would repeat. Okay, and all of these steps are sort of reasonably straightforward, except the second one, right? And of course, that's sort of the main one where we want to make use of kind of standard algorithms for deep RL, policy gradient techniques, and the likes. And where we basically would do all the planning sort of introspectively, right? We're happy to invest a bunch of compute, right, to kind of update our behavioral policy as long as we're sort of careful when rolling it out. Okay, so that's sort of the main intention that we would pursue here.
data here.
Yeah.
That's action state pairs.
Yeah, so here it's basically state action next state pairs, right? Maybe rewards, we observe them. We also apply this to partially observed settings, right? There's observations and use some recurrent models and so on. We'll talk more about this later. So data in a broad sense of learning a model. Okay, so let's focus on that. Yes? Sure. Bayesian inference. Okay, so for Gaussian process models, right, it's literally just calculate your posterior GP. We can sort of analyze this coverage for any sub-Gaussian observation model, so it doesn't have to exactly be Gaussian and so on. Okay, so this is where approximate Bayesian inference would come in, right? So using probabilistic ensembles, as we've seen earlier, right, or epistemic neural nets, whatever favorite uncertainty quantification you have, it's going to be hard to prove something about, right? But where one can use these algorithms and the algorithmic ideas to scale to more complex tasks. So the setting that we will be able to analyze is the GP setting, right? So RKHS dynamics. Okay, so now the second step, right? How do we pick our policy? So of course, what would we like to do, right? So our standard objective in RL, say for now, let's not worry about constraints. We'll put them back later. So now let's just talk about optimizing rewards. So we'll have some kind of long-term expected returns, maybe in a discounted setting, or infinite horizon average rewards settings and the likes in the true environment. Okay, and so standard approaches in policy gradients basically assume kind of sample-based access to the real environment, right? You at least need to be able to sample trajectories. If you're a simulator, that you can do, right? You can basically roll out simulations in the simulator to construct stochastic policy gradients for this object, right? That's basically what model-free kind of actor-critic methods do. We don't know the environment, so that's the assumption we want to relax. Okay, so now one natural thing is to sort of try to learn a simulator, right? And so in this Bayesian setting, maybe you get just a point estimate, maybe the most probable model or some regularized estimate condition on the data that you've collected so far, right? And once you have kind of a learned simulator, basically now you just, in a way, can use any method you like in order to kind of optimize a policy. You could use a model-free technique, a policy gradient technique, for example, to optimize in this estimated model. The trouble is, policy optimizers are very good. It's also very good at kind of dynamics hacking, right? Sort of exploiting inaccuracies of the model that's been misestimated, right? So there's some major robustness issues that often kind of plague model-based RL approaches. And the second one, of course, even we might use exploration to kind of optimize this objective, but exploration is only for the sake of optimizing kind of this empirical objective, right? So in the end, of course, we want to do well in the real world, not our estimate of the real world, right? So there's no explicit incentive to explore. Now, one technique to get around this robustness issue, we already heard advertised in David's talk earlier, right, is to take the uncertainty in this dynamics model and average it out. Okay, so that's the heart of the Pilko method, using Gaussian process dynamics, using moment matching, PETs, using probabilistic ensembles, and a whole bunch of techniques sort of around it. Okay, and that really helps dramatically with robustness, and these sort of methods often actually work very well, are quite sample efficient for quite challenging tasks. They're still amenable to standard RL solvers. Maybe you'll have to do forward propagation, so it's a bit more expensive, but you can sort of still use standard policy gradient techniques. But of course, there's no incentive to exploration. And so that's going to be the focus of what we want to talk about next. And here I want to come back to some of the work that Emily talked about earlier this morning, right? So of course, the central principle to exploration is optimism, right? And now one way to think about optimism in RL is to kind of be optimistic among all plausible NDPs, right? All plausible dynamics models that are consistent with the data that we would have so far, right? So we could try to optimize over policies pi over all dynamics F tilde, right, that are supported given the data we've collected so far of the returns, right? So that's UCRL or UCVI and so on. And so for tabular MDPs, that can be done tractably, right? And we heard about it earlier. So the question is, how do you do this with complex nonlinear dynamics models that result from GPs, neural nets, and the likes? Okay. And so the problem is that this is a really nasty, not just non-convex optimization, there's non-convex optimization everywhere in RL and deep learning and so on, right? But it's also a very nasty non-convex constraint to deal with, right? In this set. Okay. And it turns out kind of the idea very similar to sort of these exploration bonuses used in UCB can also be used in this context here. Okay. And so the idea is to basically, instead of optimizing over kind of this optimistic MDP, what we can do instead is just optimizing an empirical objective on a modified reward function. So the reward function is now basically just the standard immediate returns, RFST, plus some exploration bonus. And that estimation bonus is simply kind of the epistemic uncertainty in the dynamics model. Okay? So basically, if you think about Gaussian process dynamics models, in a way, just a L2 norm of the predicted variance. Okay, and so what we can show is with proper tuning, this indeed yields valid upper bounds. So it's a valid optimistic objective. And it's kind of not too loose of an upper bound in the sense that one can actually sort of bound the regret of that algorithm over these episodes, both in kind of the episodic setting where the agent is reset to the starting state distribution, and under some additional assumptions, even in sort of the non-episodic setting, where basically these episodes, for each episode, you don't actually have to reset the agent, but you basically just restart an episode in whatever state the agent is in. So really, in some sense, allowing kind of online learning of that resulting policy. So what's nice about this is that this now you can plug into basically any favorite model-based RL algorithm that you would like to use. So MBPO, for example, a Tremer, and the likes. Right? So all that happens is you can use sort of standard architectures for model-based RL, but instead of just optimizing the immediate return, you also kind of estimate epistemic uncertainty and add it as an exploration bonus, kind of with proper tuning. And that can really help sometimes. So for a lot of the benchmarks in RL, you don't need to do a lot of fancy exploration, right? So they're kind of very well engineered with very carefully shaped rewards that kind of just standard, say, Gaussian dithering and sort of local search often finds good solutions, okay? But if you look at sort of harder exploration tasks, maybe with particular sparse rewards or action penalties, for example, wide policy gradient techniques often converge to doing nothing, or sort of some of these difficult exploration games and the likes. If you're not careful about exploration, you're not going to get anywhere, right? And that's a very simple kind of exploration term that actually allows to find good solutions. So now coming back to constraints, right? So this was so far was about rewards. How should you think about constraints, right? And now one natural way to think about constraints is to have an explicit notion of a constraint. So it's a constraint MDP. It's a particular form of multi-objective RL, right? With one objective and one constraint. The only aspect is that second constraint we are never allowed to violate, right? So it has very specific semantics. And standard constraint MDPs are quite well studied, not as well studied as standard MDPs, but as scalable algorithms. Also policy gradient techniques for CMDPs, typically, again, assuming sample-based access to the environment, right, to the simulator, right, where you can basically unroll trajectories as much as you like, right, to construct, say, gradient estimates. And so that's what you want to, so where do the constraints come from? Well, they might indicate visiting unsafe states, for example, right? That's quite natural. So you can sort of model chance constraints, one has to be a bit careful here. They could model sort of proximity to the safe region, kind of barrier functions and the likes. So I'm not going to talk too much about cost design. There's some very interesting questions that I'd be happy to talk offline about as well. But let's go with this, right? So, and now kind of a natural way to relax this assumption that we know the environment is to apply, of course, a similar rationale, right, to exploration, to say, well, let's consider all plausible MDPs, right? A set MN of plausible dynamics, right, that are consistent with the data that we've collected so far, right? And say, well, instead of maybe optimizing or sort of considering our reward, maybe let's be optimistic with respect to our reward, but at the same time, maybe let's better be pessimistic with respect to constraint satisfaction. Okay, and again, this is this nasty non-convex constraint, but using similar ideas that I've described to you before, one can turn this sort of into a standard CMDP and throw sort of policy gradient algorithms at it to try to solve it. Now, this is sort of like mimicking what we've talked about, kind of safe Bayesian optimization. Remember the sort of this green set of plausible optimizers that's contained within this red set of sort of kind of pessimistic safe actions. So one missing piece we had discussed there was this notion of expansion, right? So maybe sometimes it's not enough to kind of only be optimistic about the rewards, but kind of really maybe go beyond, right? And really see what states can we safely reach. And that same kind of idea can also be explored in the context of model-based RL. So here's sort of a cartoon picture. So if you take the set of all policies over here, right? Yeah. Yeah.
JC is entirely a different kind of beast compared to J. Non-convex, non-everything.
J as well, right? So it is not necessarily convex, right? But
so that somehow, I mean, when you think of a reward, the reward somehow depends on all of the states of the system, but constraints sometimes are just only on the projection, only on the subspace.
Yes, absolutely. So it might be much sparser, right? So maybe kind of being more, so that's also where I think the sum of the uncertainty quantification becomes even more important. So one effect one gets from this intrinsic reward terms is exactly that, right? That basically both for rewards, if you have sparse reward terms, what happens, right? You essentially zero everywhere except for kind of close to the goal, right? But sort of that naturally emerges if you sort of think about kind of this intrinsic reward term sort of there, right? So intrinsic cost term in some sense, right? So sort of, okay. Good. So basically here's the set of all policies, right? Among them, there's some feasible ones, right? According to the F star, right? The true environments. And maybe there's a starting policy. And there's kind of this orange set of states that you can certify as safe given the data you have so far, right? This red set that we had talked about before. And now this problem of how to get from kind of pi 0 to the optimal policy on that red set, that's just a standard RL problem, right? So exploitation to sort of try to get there, right? And that's where one can use this algorithm that we discussed on the previous slide. The challenge is how do you get from here to here, right? How do you kind of push the boundary, right, and visit states that you can safely reach, but that are maybe not plausibly optimal. Okay, so basically, right, how you can sort of expand. If this is your current policy, right, how do you sort of explore to kind of learn more about the boundary, right, and hopefully eventually sort of encompass that feasible, reachable solution. Okay, and so again, intrinsic rewards to the rescue. So you can use the same intrinsic reward term, right? It's basically just the epistemic uncertainty of the dynamics model. So the L2 norm of your posterior variance, so the Gaussian process or posterior standard deviation in the Gaussian process case, or heuristic approximations in the context of Bayesian deep learning, to the extent you want to trust the uncertainty that comes out of them. And then basically you just optimize it under kind of the safe set, right? Under the set MN of plausible, SN of plausible, kind of pessimistically safe policies. Yeah. Absolutely, right? So again, as part of the prior assumption, if this red set is empty, you're out of luck, right? So that's sort of part of the assumption, right, that there is at least one kind of feasible initial policy. And where that comes from is a whole separate interesting question, happy to talk more about. Yeah, so. Well, you need to have one to start with, right? So that you need to know, absolutely, right? Or you need to have a model that allows kind of to find one, right? So that's red set needs to be non-empty. So that's basically the point. Okay. Good, right? And so now basically this optimizing that epistemic uncertainty term now basically allows to kind of expand that safe set, right? And eventually we'll actually find a near optimal reachable policy. Here's kind of the analysis from the paper. So basically there's a notion of kind of reachable sets that you can get to after a certain number of episodes. And there's, of course, a bunch of assumptions, primarily, of course, these regularity assumptions that we talked about before. And then basically under those, with this kind of scheme that I've described, one can guarantee safety with high probability and kind of near optimality. So identify an epsilon optimal policy among kind of the set of states that you reach after a number of samples that does depend on kind of this information capacity term that I've described to you earlier. That kind of came from the Bayesian optimization and kernelized dependent literature. Okay, so here's some demonstrations on sort of the simple cartpole model, right? So you want to swing up that pendulum here. The twist is you don't want to hit the red bars, right? That's the constraint, neither with your card nor with the pole. So first, an algorithm that kind of does model-based exploration, but without worrying about the constraints. So basically, here's kind of the two-dimensional state space of the angle and the position of the card. You want to reach that swung up state. And basically, with relatively few episodes, you kind of figure out how to do it. But you violate these constraints. And if you kind of use this algorithm that I've described to you before, you manage to sort of explore the state space almost as kind of efficiently without actually violating any of these constraints. So here's somewhat more complex examples, still very stylized examples, right, from these benchmark environments. So this is the safety gym benchmark suite. There's a bunch of kind of very, very stylized robots, like a point mass or a car, or a simple quadruped model that solves kind of some very interesting tasks, like reaching a goal or touching buttons, or pushing a box to a goal, and so on, from sort of forward-facing camera that's mounted on the simulated robot. So there's partial observability here. So you use some recurrent state space model, the same architecture that's in the Dreamer algorithm. And we sort of do heuristic uncertainty quantification using SWAG, that's sort of a stochastic weighted average gradient. So basically run SGD when training the model. And instead of just getting a point estimate of your weights, you keep track of the first and second moments and treat it as a Gaussian. That's sort of the way that algorithm works. And basically here's a bunch of comparisons. So the first one is CPO. So that's a pretty good model-free CMDP solver, right? It's kind of the constrained analog of PPO. Optimize a very similar sort of loss. In terms of computational efficiency, it's a very good algorithm. It kind of often finds very good solutions, but in terms of environment interactions, it's of course very slow, right? And that's the primary benefit one can get with these model-based techniques, that they're basically able to be much more efficient in terms of environment interactions. Not in terms of computational cost, but in terms of environment interaction. So here's the previous kind of state-of-the-art model-based CMDP solver, and here's kind of this log barrier-based one that we've described to you before. So you can basically essentially kind of find a feasible policy here a little bit later in terms of reward, but maintaining safety during learning. So here's a bunch of other tasks from the safety gym benchmark suite, from the humanoid bench, where you have to sort of have this highly stylized humanoid that sort of shouldn't run into these poles and so on. Okay, now here, like a little bit more realistic setting. I'm sure you'll see many more exciting videos tomorrow in the talks. But to kind of demonstrate this on a physical platform, at least, in collaboration with Stella and Cora's group at ETH. So the task is pretty simple. So you take this RC car, you want to reverse park it at a designated spot. So it's not a super complicated control problem. But it's one, if you really want to simulate this precisely, you have to worry about kind of slippage, material effects, aerodynamic drag, and so on. Okay, so if you want to really build an accurate enough simulation model, it kind of is more involved somehow. And if you use a simplified model, basically a bicycle model, sort of, right, low-dimensional approximation of this, then and just estimate your simulator and optimize the policy, right, using policy gradients in simulation, of course, there's going to be a gap. That's not particularly surprising. So you really would use feedback controllers and so on to solve that task. Okay, now here's basically a model-based RL completely from scratch, knowing nothing about physics, right? So it's using a very uninformed prior that's regularized towards just an uninformed Gaussian process prior. The first couple episodes, right, it doesn't know anything about physics, so it spirals pretty wildly out of control. After about 15 episodes, figures out how to reverse, and then about 20 episodes later, it actually solves the task. Now that said, right, for this task and for many others, there's a lot of prior knowledge we would have, right? Why would we want to sort of learn physics from scratch, right? And of course, there's a lot of really exciting work, and we heard about some of it in this workshop today, on how to sort of infuse physics in these types of models. Okay, now one technique that is extensively used, so to kind of address the sim-to-real gap in robotics, to the extent that I'm aware, is domain randomization. So what you would do is you would basically not just simulate a fixed MDP, right, but vary it slightly, change different mass constants, different environment constants, and the likes. Sort of randomize over different environments. Okay, and so then you sort of train a policy, right, on that domain randomized simulator, and that buys you a bit of robustness and so on, right? So that's kind of often a very good idea, right? Now, one kind of natural thing one could try to do is one could sort of try to use domain randomization as a prior, right? So here we do Bayesian inference. If you use an uninformed prior, it might take longer, right? So let's use sort of a physics-based prior that kind of captures in a way that inductive bias that comes from domain randomization. And you can do this through hierarchical Bayesian inference. You can basically learn kind of a prior distribution over dynamics models that has sort of the same statistical signature as domain randomization. So I'm not going to go too much into details of this, but essentially what you do is you basically simulate, like do domain randomization, really. So essentially just simulate a whole bunch of basically simulations that sort of captured what you would expect as natural variability in the environment. And basically we try to match the marginals of that process. Okay, so marginals, of course, not just one-dimensional ones, also not just two-dimensional ones, right? For a Gaussian process, these would fully characterize the system, right? Where you have all pairwise marginals being multivariate Gaussian, kind of their correlation capturing the smoothness properties. So what you're going to do is basically sort of try to capture multivariate marginals just by using a big neural nets, right? That sort of extracts in a way the statistical signature from these simulations using score matching. And that is basically now serving as a regularizer. So we can use it to basically regularize the learning process of this data-driven model. And there, kind of even in the first episode, we sort of go in the right direction. At least we don't spiral out of control. After 5, it turns around. After about 10 episodes or so, it solves this task. And so it here just keeps refining this a little bit more. Okay. And so here's just sort of a couple of more quantitative results about this. So this plot on the left, this is not closed loop. So this is basically collect training data, holdout data to predict dynamics. The x-axis shows as we get more and more training data, how does your test set negative log likelihood improve? This first one is just using identification on an underspecified model, right? So it's no surprise that we can quickly learn it, but eventually we can outperform it because it doesn't capture sort of the details of the environment, right? There's materials properties and the likes. This is uninformed prior, so it starts off much worse, but eventually gets better. A natural kind of baseline is gray box modeling, so we would maybe identify the model and then just learn the delta, right? So the deviation from that model. Starts off better, and basically that inductive bias helps you learn more quickly. But using this kind of domain randomization prior, you not just start at a better place, but you find a better solution in the end. And here's kind of the quantitative version of the video I showed before. So the two curves are basically the just standard uninformed versus the physics-based prior that I've described, right? So you start already with a better policy and then find a feasible one more quickly. Okay, so how am I doing with time? So I guess we're pretty much out of time. So there's, yeah, okay. A couple slides about language models if you want, but I can also skip that part. But okay, so good. So now, of course, one application of RL where a lot of people are excited about these days, right, is AI systems, language models, right? And of course, they're pre-trained to do imitation, right, to do next token prediction. And RL is used to align these models with human preferences, right, to maybe produce summaries that you might like or jokes that you might find funny, and so on. They're also, of course, using RL and algorithms like GPO and so on to optimize quantitative sort of basically verifiable tasks like correctness of solutions to math problems and the likes. Okay. Now, of course, these models also behave in all sorts of ways that we don't want them to, right? Producing all sorts of toxic output, for example. And so now a question is kind of how should we think about safety in the context of these language models? And so there's already kind of quite some connections sort of built up on thinking about generation of language models through the lens of reinforcement learning. So it's pretty natural to think about, is there anything we can do about sort of constraint RL and constraints? And so that's something that we've been starting to explore, and there's a paper coming up at ICML. Basically, the key challenge, of course, in this domain is it might be very hard to write down kind of the constraints ahead of time, right? So that the model shouldn't produce whatever fraud or misinformation or bad jokes or whatever, right? And so we, of course, want to learn those constraints from data. And there's, I think, a lot of really exciting questions around this question. So there's been a lot of work on sort of inverse RL, sort of trying to, in a way, from demonstrations, maybe a little bit of labeled data, can you sort of reverse engineer what's the underlying reward function? there's been much less work, but I think it's super important to also learn about sort of constraints. And so that's happy to talk more about this later. So here we actually learn from labeled data. So where basically we take a bunch of data set of sort of unsafe, undesirable behavior of language models that someone annotated, and then basically try to learn safety constraints. And then what we can do is sort of at test time, basically try to kind of back project, right? To kind of use these learned constraint sets as sort of a safety filter, right? To kind of go back to the feasible region. And so the way we do this, we learn this is basically just learn linear constraints in a suitable feature space. So we don't take the language model features directly. We sort of have an additional sort of encoder, a sparse autoencoder, that is a very small neural net that just takes the output of the features, but kind of that's an architecture that's been quite effectively used in the interpretability literature. And we train it jointly with basically this convex polytope machine, right? So in a way, kind of a unsupervised generalization of support vector machines that basically tries to learn multiple safety constraints that describe sort of that safe set. And so here, what this experiment shows, there's a data set called Beaver Tails, contains like, I think 330,000 examples of unsafe quote unquote behavior of language models that have been annotated according to a bunch of different categories that you can see here on the left-hand side. And basically the right-hand side shows kind of the constraints or the facets that are violated from kind of the safety model that is estimated here. And of course, you can also, so in a way, it discovers kind of things that might go wrong, right, from annotations. And so these annotations are very naturally collected anyways, right? So most language models and sort of chatbots, you basically can flag, right, if they output something that they shouldn't have. And so here's sort of a performance kind of accuracy. So kind of the trade-off between how well do these models still perform versus kind of how well are they able to detect potential attacks, right, or unsafe examples on a bunch of different open language models like Llama 2, Ministral, Qwen 2, and the like. So each of these plots is basically a trade-off curve between the rate at which certain kind of attacks were able to basically be kind of defended against by back projecting onto this safe set. And the y-axis basically shows the accuracy, right? So how much kind of how well does the model perform on sort of the standard knowledge basis MMLU, where it's a common benchmark testing sort of general understanding of these language models to what one can say. So you basically want to be on sort of the top left side here, right? Have kind of low attack success rates by not dropping too much in terms of performance. The original model is here, right, on the bottom, on the top right, does pretty well, but pretty susceptible to these attacks. And here, essentially, you can get pretty substantial improvements in terms of this attack success rate without too much of a drop in terms of accuracy. Okay, so now, of course, there's no attacks that sort of try to specifically attack this defense mechanism, right? And of course, that is a potential major attack surface. I want to be clear about this as well, right? This is purely sort of statistical generation based on generalization based on data that's been collected. Okay, so that's basically all I have, right? So I think if you really want to get closer to this cartoon of RL, right, of an agent that really learns reliably online, adapts, right? I think uncertainty quantification is key. If you don't know how the world works, every action is exploratory. And uncertainty quantification is something where even the current best foundation models that are out there are generally not very good at. So that I think is a major area where a lot more work is needed. And I think so reinforcement learning can substantially benefit from that. Just a quick pointer. So there's a large initiative in Switzerland catalyzed by the new high performance computer in Lugano with a bunch of GPUs that's open for collaboration where we're really training large foundation models with applications in robotics, but also other domains as well. Okay, so thank you very much and looking forward to your questions.
Yeah, thanks to Andreas for the very nice talk. So we are ready to have questions. So
So I have a question, and I guess, okay, two ways to ask. Let's go with the intuitive one. So I guess it can happen that your global optim or there is a good point that you cannot reach because you're not sure that it's safe, and also the things that are are safe are not helping you to figure this out.
Absolutely.
And is that also what you were saying when you said reachable in the theory?
Precisely, exactly.
So
that's the benchmark. So there's the notion of sort of expansion we defined. I briefly showed it in a slide, right? But essentially, it's sort of like the incorporation of additional data, right? To what extent it allows you to sort of push the boundary of the safe set, right? You can sort of define an operator that expands, right, in a way based on individual measurements, and you can iterate that operator, and there's a closure of that, right? That the optimum is defined with respect to that sort of the.
So it seems you might leave a lot on the table.
Sure.
Is there an escape hatch that you can?
So absolutely great question. There has been also quite a bit of work on this already now. So there's some work on sort of if you can fail a small number of times, if you can crash a small number of robots, where should you sample in order to sort of try to find islands of where you could do better, right? That's one way of how one can think about this. There is also some very nice work out of Sebastian Trimpel's group where they looked at something is not quite model-based RL, but sort of looking at dynamics specifically and kind of serendipitously using the fact that if you have dynamical systems and they visit kind of state sequences, if kind of they successfully solve their task, you can infer that all states visited along the way are safe, right? And you can sort of use that to further kind of expand the set of reachable states and so on. So there's quite a bit of follow-up work on that. But so a very interesting question.
Thanks for the talk. So I have a question regarding this safe regions. So I guess like safe spaces in terms of like physical world is very different from the parameter space. But I'm just wondering, so it could probably be that there are like some safe regions are destroyed. And I'm just wondering whether this Bayesian methods are able to like jump over.
Sure.
Yeah.
Okay, great question. So I think it also connects to what this question, right? So to some extent, so what happens if then kind of the safe region is disconnected and so on? In some sense, if you kind of have sufficient prior information, right, to conclude that that region, right, even if it's disconnected, but kind of you have whatever can pessimistically certify safety in kind of the right connected components, that's still fine, right? So the question is more like what happens if there's something good out there that you just can't conclude based on the assumptions that you've made about the system, right? And then the question is, what can you really hope, right? So the only way I think is then to really allow some amount of constraint violations and so on. But in general, of course, yeah, so the question is, where do these constraints come from, right? Maybe one can hand design them, but I think also very interesting questions that I alluded to for sort of inverse safe RL, right? How do you maybe learn what's safe from demonstrations and so on?
Thanks.
Sure.
Just to follow up on that answer, could it be possible that it could be the converse, which is that because your safety violation is so severe for the specific reward that you're trying to achieve, you just need to totally look for other rewards which are sort of in that space, not necessarily those maybe that are amenable to a GP type of uncertainty, but something where you're drastically, like for instance, again, sorry to keep coming back to a flight control example, but stall, for instance, is a total no-no. And if you're trying to meet that constraint, you have to totally relax some of the reward specifications that you have in terms of your rates, and only then can you achieve. So then that might not be at all within the reward space that you started out with. And so you have to look for a totally different cost fund. I mean, I don't know if those kinds of things are within the realm of what you're trying to do.
Absolutely. So I'm not saying one should use that algorithm as for flight control, okay? So, but I think there's a lot more, right, that needs to happen. I think the ambition maybe now is to have algorithms that are more robust, right? Sort of get closer to this cartoon, right, that are completely described. Now, so what I've described about a safe expansion is reward-free, right? So at least the basic algorithm I've described, just optimize an epistemic uncertainty term, right? So it only uses the costs, right? And so this is the result I showed about optimality is some exploit and commit kind of strategy, right? So you figure out kind of all you can about the dynamics, right? And then you commit, right? By optimizing just based on a point estimate of the data you collected so far. So in that case, right, if kind of you can't find a good enough solution, maybe that's a signal that your reward function is wrong, right? Also, but
So for the optimistic model-based RL algorithm, you propose an explicit form for the intrinsic reward you have to add. So you have then benchmark with deep RL algorithm. So I know that in deep RL they also try to learn this intrinsic reward with a neural network. Did you compare to this type of? I don't know if it's popular, this random network distillation principles and all these things.
so there's a whole, I mean,
Yeah,
huge around kind of exploration bonuses, right? And curiosity and whatever have you also, right? We haven't done sort of an exhaustive comparison. So here the main point is this is a very simple term, right? And it's a very natural connection to, right, optimism and so on, right?
Okay.
And so it doesn't say it's the single best thing one could do, right? The primary motivation that I mentioned is of course safety, right? And if you kind of really to get
of
right
course.
certifiable pessimistic cost estimates, right, that you couldn't get, I think, from any of the from the in this case, kind of pessimism bonuses or whatever, right? So
thank you.
I should say maybe some kind of related pessimism ideas, of course, have been used in offline RL as well, right? And that's also connected. I forgot to mention that before. So.
Yes, thank you for nice presentation. By introducing uncertainties, you also increase numerical complexity of problem massively, I think, yes?
No.
No.
I don't think so. No, so the additional computational cost is pretty small if you already commit to model-based RL. Okay, so if you compare the cost of, say, Dreamer, right, and this kind of using this exploration bonus or MBPO or so, it's not a lot of overheads, right? So again, if computation is the primary concern and you have a good simulator, use PPO or SAC, right, or sort of one of the standard policy gradient algorithms. So CPO maybe if you have constraints. So this is really here. You want to be careful with rollouts, right, in the real environment, right? So kind of really learning online.
Okay, thank you.
Okay. It's also maybe just a comment, right? So I made this analogy with Bayesian optimization, right? But that's kind of a primary motivation of kind of techniques around Bayesian optimization, that you're happy to kind of invest some computation to optimize an acquisition function. It's so cheap compared to carrying out your wet lab experiment, right? Or running your robot or whatever, doing an experiment on the free Electron laser or so.
Probably I'll have one question.
Yeah.
Like at the point you are mentioning safety is typically taken as an anytime condition, right?
Yeah.
And like when we put it in the constraint, we typically put it as a cumulative constraint and a cumulative reward, right? This is often like what we have done also, like that's a typical thing.
Sure.
But is there like any kind of example where there's a conflict between having this instantaneous condition and having the
Yeah, so, okay. I mean, the formalism here is CMDPs, right? And that's sort of an average cost in terms of safety, right? That may or may not be appropriate. Now, I briefly mentioned it before, right? But one can actually relate cost design to state-wise safety constraints. So there's some work from a postdoc of mine, Armin Lederer, who looked at that, right? How do you kind of choose costs if you really want to ensure state-wise safety constraints and sort of still treat it as a CMDP? So to some extent, that is sort of possible, right? You can sort of design certain barriers to kind of, but yeah, so what's the right formalism? Yeah, so one can maybe argue a little bit about. So we've done some other earlier work on kind of using the same principle of sort of quantifying the epistemic uncertainty in a dynamics model, but then sort of trying to explicitly verify, say, the decrease condition of a Lyapunov function or something like this, right? That's one can also do, but it's computationally much more involved and so on.